Hello and welcome to another power electronics class. In the previous class, we finished the DC to AC, the inverters, and we solved a problem for that as well. And today, we will start with the AC to AC converters. And specifically, we will start with the AC voltage controllers first. And if we have time, we will continue with the frequency controls as well. So the contents of this lecture, for today's lecture, let me zoom in. We want to cover the basic AC voltage controller circuit, the AC phase control chopper, and the AC voltage controller characteristics. So we will start with the AC choppers. It's a power electronic AC to AC converter in its generic form. And the input is an AC signal. The output is also another AC waveform, but they may differ or change in amplitude, frequency, or phase. It may be single phase AC to AC or a three-phase AC to AC converter. AC to AC converters can be categorized into three topologies. We have AC to AC voltage controller converter, which are mainly the AC choppers. We have AC cyclo converters. We have matrix converters, which are divided into two subcategories of indirect matrix converters and direct matrix converters. Now, here you can see the topologies for the AC to AC voltage controller. We usually have an input voltage and a frequency. An AC to AC voltage controller converter only changes the voltage, the amplitude of the voltage. Usually the RMS voltage changes, and the frequency is fixed. The frequency would not change. So if you give it a 60 hertz, 220 volts, the output could be 100 volts, but the same frequency, 60 hertz. Then we have the AC cycloconverters. We have an input voltage and frequency. Imagine we have a 220 volts. So for the first one, 200 volts, for example, 60 hertz. The output will remain at 60 hertz, but the voltage may go to 400 volts, for example. So the frequency is fixed, but the voltage varies. For a cyclo converter, you have an input frequency and voltage, for example, 200 volts, 60 hertz, and then we would have a variable voltage and frequency. So the output could be 450 volts at 50 hertz. And it may have a unidirectional operation as well. So if you have, for example, a wind turbine, this is a good option to use. And finally, we have the indirect and direct matrix converters. We have an input voltage and frequency. Again, for example, imagine we have a 200 volts, 60 hertz input. But here we have a variable voltage and frequency of, let's say, the output is 460 volts, 70 hertz, but this one is bidirectional. So AC cycle converters are unidirectional. The matrix converters are bidirectional. So one is good if you want to just, for example, control a motor speed. AC cycle converters are very good. The matrix converters are good if you want to connect a grid-tied power power plant, for example, or a power generator like a wind turbine to the system. Now, you may ask, what is the point of an AC voltage controller converter? We have another device for that, to convert AC voltage. What is that device? Do you remember? Yes, a transformer. A transformer is a very simple, easy, doesn't require any controllers, and we have different type of transformers for different applications, and we can easily alter or vary the output voltage depending on the number of turns that we have. So we can build the same thing, that we can have a 200 volt input and a 400 volt output. And we have another device called the auto transformer, and the auto transformer, we can actually change the ratio between the input and output. Usually I will show an auto transformer in the lab. It has a knob on it, and you would turn the knob and you can adjust the output voltage as well. But the thing is, this auto transformer, you don't have a lot of control over it. So if you want a real-time, very fast system to be able to accurately control the output voltage, auto transformer is not very useful. But for fixed applications, obviously auto transformer is the way to go. Less complication, very simple, very reliable. It lasts for a few decades if properly maintained. So in a grid, definitely transformer, because you need to have a fixed ratio. But sometimes you need to change that ratio. For example, if you want to dim a light, then AC to AC controller converters are the way to go. And when you want to control speed of motor, sometimes we use AC to AC converter, or anything that we want to have precise control over it using a microcontroller. The AC to AC voltage controller is a good option. But usually we use that to control lights, like dimming lights and so on, because auto transformers are bulky, heavy, and sometimes they're much more expensive, require a lot of copper, and therefore we go for an AC to AC. They are much smaller and cheaper as well. Nowadays they are very cheap, actually. Now, these pictures show the diagram for the mentioned converters. On the top left, we see an AC to AC voltage controller converter using 3 thyristors, 2 of them. On the right of that, we have the cycloconverters. On the bottom left, we have indirect matrix converters, and on the bottom right, we have direct matrix converters. So in this course, the first, second, meaning the AC voltage controller, the cycloconverter, and the indirect matrix converter would be covered. We will start with the first, which is the AC voltage controller, and requires a device called the AC chopper, and we call them AC choppers. So what are the AC choppers? AC choppers are AC voltage controllers, or in other words, AC line voltage controllers, and they are employed to vary the RMS value of the alternating voltage applied to a load circuit. By introducing thyristors between the load and the constant voltage AC source, the RMS value of alternating voltage applied to a load circuit is controlled by controlling the triggering angle of the thyristor or triac in the AC voltage controller circuit. We have 2 different types of thyristor control to control the AC power flow. We have the on-off control, and we have the phase control. So as mentioned, I already mentioned a few applications of voltage controllers, AC voltage controllers or choppers. They're mostly used in lighting, illumination control, and AC power circuits. We also use them in induction heating. We use them in transformer tap changing or on-load tap changers. And sometimes we also use them in speed control of induction motors. The last one is recently with the improvement in IGBTs, we don't have that much of choppers for controlling induction motors. We are just straight out using the inverter system right now. So this is a basic circuit that could be used for an AC chopper. This is a circuit for a triac light dimmer. And a light dimmer, obviously, if you have higher voltage, you're going to have a brighter light. And if you have a lower voltage, you're going to have a lower light or lower lumen, I would say. And in this system, we usually have a fixed frequency of 50 or 60 hertz. And by changing the firing angle, which is controlled by a potentiometer, we can control the output voltage. The output is usually connected to an RC circuit and a diac. A diac, by the way, is a bilateral trigger diode, which we call it the diac. And on the right here, you can see a triac or front view of a triac. And it's something like a transistor, a little different than a transistor, actually. And actually, it's a bilateral trigger system, the triac as well. The way that this works, this is a very small explanation. By the way, you can see the light bulb over here or the load. So what happens is during each half cycle, the voltage across the capacitor, if it exceeds the breakover voltage of the diac, it fires the triac. So if this voltage goes higher, it's going to trigger the triac. And then what happens is the current would actually flow through the load. And the RC timing of this is related to this 250 kilo ohm potentiometer and this 3.3 kilo ohm resistor. By changing this linear potentiometer, we can change the RC and therefore the omega C of this system, and change the phase delay of this system, and therefore change the triggering time of the diode. And therefore, by just controlling a simple small potentiometer, we can control how much power is going to the output. It's very similar to the switching that we had in DC. The only difference here, instead of having a switch, we have a triac and a diac, and we control the trigger with the potentiometer. Okay. Now, this picture shows the output of this triac and the output power that it actually delivers and the output voltage of the capacitor. So the black line shows the source voltage. The blue one is the capacitor voltage, and the red is the diac breakover. So you can see when the capacitor voltage reaches the diac breakover, so it charges until it reaches the diac breakover, then it immediately is short circuited, therefore it's discharging, and then again it's going to charge in the opposite direction, discharge, charge, and so on. Why? Because we have a positive, negative, or an AC signal. So very similar to what we saw in a rectifier as well. But in a rectifier, it wasn't just a positive cycle. This is a positive and negative cycle. So again, the capacitor charges and then discharges and charges and discharges. And each time that it charges and it reaches the breakover of this one turns on. When this turns on, the light bulb is connected to the output. Now, depending on the potentiometer, we can change the fire angle. So by adjusting the potentiometer, we can adjust the fire angle and therefore control how much output voltage we want to give to the system. By the way, this voltage that you see is only the capacitor voltage. It's not the output voltage. Don't confuse it with the output voltage. I will show you the next picture actually shows you the load voltage. Now you may ask, in an RC circuit, we can change the capacitor and the resistor to change the fire angle. Why didn't we use a variable capacitor? Variable capacitors are very expensive, okay? And they are very difficult to make, and they're not reliable. And also they are extremely sensitive to heat and shock. So a capacitor, if we want to build a variable capacitor, just for your information, the capacitor's capacitance is depending on the area and the distance between these two and the conductor material between it, okay? So I'm going to call this sigma, D, and A. Obviously, we cannot change A, the area. We cannot change the material between it. Usually it's air or like some type of silicon or something like that. The only thing that we can change in a capacitor to build a variable capacitor is this D. And this D is usually around like few millimeters down to few micrometers. So a very small vibration would change the distance between these two, therefore change your capacitor. So the better option is always to have a variable resistor, which is much easier to build, okay, or a potentiometer. Now, changing that potentiometer, we can change the fire angle from 30 to 90 to 150 degrees. So 30 degree, you preserve most of the inputs you deliver to the output. 90 degrees, it's around half, and 150 degrees is around 1/4, you can say, okay? What happens if the fire angle is 180 degrees? What would we see in the output? 0. So if you add 180, and by the way, you can see here 180 degrees, at 180 degrees, the output is equal to what? 0. What if the fire angle was 0 degrees? Then what would happen? If alpha was 0 degrees, then V out would be equal to V source, okay? So at 0 degrees, and by the way, 0 degrees here, when it's 0 degrees means this is turned on all the time, okay? It's just turned on all the time. Immediately it turns on. If it's 180 degrees, the triac is completely turned off, okay? So when it's 0 degrees, completely turned on. When it's 180 degrees, it's turned off, completely turned off at all the cycles. Now, the RMS output voltage can be found using the following equation. V square AB RMS is equal to V square AN RMS, 1 minus alpha over pi plus sine of 2 alpha over 2 pi. By the way, these are just brackets. Now, this graph shows the power delivered based on the firing angle, or alpha. So you can see here that at 0 degrees, the maximum power would be delivered. In other words, the power delivered is 100%. Okay. What about 90 degrees? What happens at 90 degrees? 50%. Thank you. And what happens at 180 degrees? It's 0%. So easily we can, by changing the potentiometer, and this is a very simple to build circuit. You just need a triac, a diac, a potentiometer, and a fixed resistor, which is going to be pretty easy to fix. But there's a problem with this. Can you tell me what's the problem with this system? So the problem with this system is that if you have a kind of motor that you want to run on AC, the output signal of this is not an AC. It's just a pulsating, it's not a, sinusoid AC signal. It's a pulsating, it's an AC signal, but here it's just a triangle that it's pulsating, okay? So if you want to run a motor, it may damage the motor, okay? But if you want to turn on a light, it doesn't matter. If you want to heat a heater, doesn't matter. But if you want to run a motor, you want a pure sine wave, the output of this is not a sine wave anymore. Okay. It looks like, a pulsating, triangle, something like that. So it's good in sub applications, not very good in other applications. Now, the first one, this chopper was based on the phase angle. We could control at which phase we want to turn it on in each cycle. There's another way as well to control the output power and voltage, which is called the on-off AC voltage regulator. And the on-off voltage controller is a technique using thyristors again. And the thyristors have a control, and they would turn on in a few cycles and turn off in other cycles. Therefore, they are connect the supply to the source and, for example, 4 of the cycles, and then cut them off at the next 5 cycles. So exactly like a DC switch that we had. Therefore, the thyristors are acting like a high-speed contactor or a high-speed switch as well. Now, this is an example of a on-off voltage controller system. Again, frequency doesn't change, and none of them frequency change. And you saw the first one as well, the frequency remains at 60 hertz. Here, the frequency is 60 hertz as well. The only thing is we would control, for example, for half of a second, the switch is turned on. For the other half, it's turned off. And this is an example that you can see that we turn on the switch for N time. So this is the on time. I'm going to draw it with the blue. And we have the off time, which is this red. And here the signal is 0. So by varying the number of N and M cycles, the power delivered can be regulated. For N on cycles and M off cycles, the period of the system is going to be N plus M 2 pi radians. So V output RMS, this is RMS by the way, is going to be N over 2 pi N plus M, the integral of 0 to 2 pi Vm square sine square omega t d omega t. And when we simplify it, and by the way, that's the square root of that, V output RMS is going to be Vm over square root of 2, which is the RMS value, times square root of N over N plus M. And this is very important. So V out RMS is going to be equal to Vs square root of N over N plus M. I want you to write this down. let's solve a practice problem here. So imagine Vs in our system is 500 volts. The on time N is equal to 12 and M is equal to 6. I want you to find V out RMS or VOR. You're going to have a question on this on, again, your next week's exam. Perfect. Yes, 408. So V out RMS is going to be 500 times square root of 12 over 12 plus 6. So this part is going to be 0.816, and the final answer would be 408.248. Now, what happens if N is 12? Let's say, sorry, N is 18 and M is 0. It's going to be square root of 18 over 18, which is 1. Square root of 1 is 1. So V out is going to be Vs. Okay? Meaning it's on all the time. And this is, by the way, we would assume we don't have any loss in the system. Obviously, you have a little bit of loss. You have a drop in the voltage, but it's, negligible here. Now, the RMS load current is going to be the RMS load voltage divided by the resistance. And the power delivered to the load is going to be equal to V square output RMS over R. In other words, because V output RMS is Vs square root of N over N plus M, then we can replace it with that. By the way, N over N plus M, we can write it as K. So therefore, the power output or the delivered power would be K square root of Vs over R. The RMS value of input current, Is, is RMS value of load current, I out. The input VA is Vs RMS value of source current, and therefore Vs Is is Vs times I out RMS, which is going to be Vs times V out RMS over R. So the input volt amp times the power factor is going to be equal to the power delivered to the load. Therefore, the input power factor is going to be V square of output RMS over R, which gives us square root of K. So in other words, the input VA is technically the apparent power times the power factor gives us the power load delivered, P. And we already know that the power factor is going to be equal to P over S. But for you, you need to know this. The input power factor is going to be square root of K. Now for this example, I want you to find the RMS load when R is 10 ohms. I want you to find the I output RMS load. And I also want you to find the input power factor. So we got the output RMS at 408.2. And the input power factor is going to be equal to square root of 12. 12 plus 6. What did you get? Perfect, 0.816. So the current is 40.82 amps, and the power factor is 0.816. Again, what happens if M is 0? Then what would the power factor be? 1, which is the perfect power factor, okay? We are overlap, which is this. Now, the greater the M gets, you're going to have a lower power factor. Therefore, it means that you're wasting a lot of power as reactive power. We want the power to be, 100% real power, S be equal to P. So as each thyristor conducts for P radians during each cycle of N on cycles, the average value of thyristor current is given by this equation, N over 2 pi N plus M, the integral of 0 to pi, Im sine of omega t. And the second part is actually going to be equal to Im over pi, N over N plus N, which simplifies to Kim over pi. And similarly, the RMS value of thyristor current, I of the thyristor of its RMS value is going to be N over 2 pi N plus M, integral of 0 to pi, Im square sine square of omega t plus d omega t, all of that, square root of that. And therefore, it's going to be Im over 2 square root of N over N plus M, which this again is K. So it's going to be Im square root of K over 2. So this is important. I want you to write this down. It's going to be Im square root of K over 2. The RMS value of the thyristor is going to be Im square root of K over 2. Now, I'm going to hand you some papers for a small quiz. Again, this is mainly for attendance. And we're going to solve a problem together. So the question is this. A single phase voltage controller has the input voltage of 230 volts at 50 hertz and a load of 15 ohms. R is 15 ohms. For 6 cycles, it's on, and for 4 cycles, it's off. So N is 6, M is 4. We want to determine A, the RMS output voltage, B, the input power factor, and C, average and RMS thyristor currents. N, like, yes, on time is N, like noodle, N. And M, off time is 4. Do you want me to go to the previous slide so you can write down the equations? Yes? So again, the equations are as follows. V output, the important ones are these ones. You want the input power factor, the output RMS, output RMS current, power factor. I don't know if it asks for the power delivered, but if it asks for that, it's going to be this KVS square over R. If you can write that down, I'm going to go to the next slide for the rest of the third source currents. The question, yes. Sorry. And these are the other. And this is the average, by the way. This is the average value of resistor. Did you all solve it, or you need more time? What are your answers? Okay. Do you get the same? Okay. What about the thyristor's average current? Okay. How much? Okay. Yes, yes. So A, the RMS value of the output voltage, V output R RMS is going to be 230 times N was 6 as mentioned, or 6 plus 4 gives us 178.157, the same that you got. The input power factor, as you mentioned, is 0.7746 lagging, which is again square root of N over N plus M. The power delivered to the load, you can use a power equation. So it's going to be I square of output RMS R, or the V square of output RMS over R, which gives us 2,116 watts, or 2.1 kilowatts. And the input volt amps is going to be, which we didn't require actually, it's going to 230 times 230 times square root of 6 over 15 gives us 2.7 volt amps, kilovolt amps. And the input power factor is going to be the same, which is 0.7746. So the input power factor gives us the difference between these, the apparent power and the real power that we had. Now the peak thyristor current is going to be Vm is over R. What is Vm? Vm is going to be Vrms of the input, which is 230 times square root of 2. As you know, Vs is Vm over square root of 2. In other words, Vm is going to be Vs times square root of 2. And Vs was how much? 230. So 230 times square root of 2 gives us Vm. And this part, this is Vm. And Im would be Vm over R, which gives us 21.681. Did you get the same answer? Okay. So again, Vs times square root of 2 gives us Vm. So 230 is yes. And therefore, Im would be 21.681. Now, the average value of thyristor current, IT average, is going to be equal to K Im over pi. K was 0.6, which is 6 over 4 plus 6, so 0.6, times 21.681, which is Im over pi, gives us 4.14 amps. Now, the RMS value of the thyristor current is going to be equal to Im times square root of K over 2, which is, again, Im is 21.68 times square root of 0.6 over 2 gives us 8.397 amps. Now, for next week's exam, you're going to have at least one or two of these questions. I will solve some practice problems before the exams. Pretty straightforward. I will give you all the equations needed for the exam, so you don't have to memorize any of them. So again, two ways. We had the phase firing and the on-off choppers. And we're going to go deep into the AC phase control choppers. In phase control, the thyristors are used as switches to connect the load circuit to the input AC supply for a part of every input cycle. That is, the AC supply voltage is chopped using thyristor triac during a part of each input cycle. The switch is turned on for a part of every half cycle so that input supply voltage appears across the load and then turn off during the remaining part of input half cycle to disconnect the AC supply from the load. Same thing that we saw in that fire angle that I showed you for 30 degrees, 90 degrees, and so on. Now, by controlling that phase angle, alpha, we can control the output RMS voltage across the load. The trigger delay alpha is defined as the phase angle as well, the value of omega t, at which the thyristor turns on and the load current begins to flow. Now we have different types of AC voltage controller. We have single phase AC controllers and we have three-phase AC controllers. So a single phase AC controller has two of these thyristors, and for a three-phase we have two for each phase, so 6 in total. We can also have other subdivisions of AC voltage controllers. We can have them as unidirectional or half wave AC controllers and bidirectional or full wave AC controllers. Now, let's dive deep into the principles of AC phase control. We will start with a half wave AC phase controller, or in other words, a unidirectional controller for a single phase system. So a single phase half wave AC controller is going to look like this usually. In this system, if omega t is 0 or alpha, again, between 0 and alpha, then V out would be 0 for this example. So we are studying this graph over here. Imagine here alpha is, let's say, 30 degrees, for example. From 0 to alpha here, we won't have any output voltage. Therefore, output voltage is 0, and Vm sine of omega t for this part is going to be equal to 0. But from alpha, for example, to 2 pi, we have an output because the fire angle here is alpha, by the way. This switch is turned on and we're going to have an output. And the output here is going to be Vm sine of omega t, depending on how much Vm is. By the way, this upper one, I'm going to draw it with, let me draw it with a different color. The red one is our voltage, and the green one is the current, okay? And again, both of them are turned off or blocked before alpha, or in other words, they are both zeros. Just they start at alpha. Now, what is the current? It's the same frequency and phase as the voltage divided by the resistor. So V out, I out or IL is going to be V out over RL. In other words, it's going to be Vm sine of omega t over RL, for omega t is equal to alpha to 2 pi. What is it before alpha? It's 0. So I out is 0 for omega t equal to 0 to alpha. Oh, it's already mentioned here. Again. Now, what is the RMS output voltage? The RMS output voltage, again, we can find the RMS the same that we did it for the on-off situation. For the on-off situation, we had a pure sine wave. And a pure sine wave, we already know that VRMS from this equation is equal to Vm over square root of 2. Since this is not a sine wave, we have to calculate the RMS, or the effective output voltage, using the equation of the sine wave. So V out RMS is going to be 1 over 2 pi integral of alpha over 2 pi Vm square sine square of omega t dot d omega t. I have a quick question. In circuits 1, did you learn how to measure and calculate RMS values? Yes. Okay. So V out RMS, so you know this equation is going to be Vm square over 2 pi integral of alpha to 2 pi 1 minus cosine of 2 alpha omega t over 2 d omega t. And V out RMS is going to be Vs square root of 1 over 2 pi minus alpha plus sine of 2 alpha over 2. So VI RMS is going to be Vs over Vm over square root of 2 RMS value of input supply voltage across the transformer's secondary winding. So the output RMS voltage for the system is going to be equal to Vs. I want you to write down this equation over 1 over square root of 1 over 2 pi minus alpha plus sine of 2 alpha over 2. This is the output, by the way. The input, because we had a pure sine wave, it's just going to be simply Vm over square root of 2. So comparing these two equations of V out over Vn, which one has a higher RMS value? What is the maximum of a sine wave? 1. What is the minimum? 0. So the maximum of this is when the sine wave is equal to what? Is equal to 1. When is sine equal to 1? Sine of what? Are you sure? Sine of 90 degrees, yes? Am I correct? Yes. So what should alpha be? 2 alpha is 90 degrees. What is alpha? Yes. Okay. So the maximum of this value, if you solve it, I'm not just going to go into the details, is going to equal to this. Okay. So always the input VRMS is going to be greater than the output VRMS or equal. The maximum that the output VRMS could go is Vm over square root of 2. Okay, and I think we can continue the rest next week because I don't have time to finish that part. Yeah, let's finish this little part and then I'll stop at the example. We'll start the example next week. So, okay. Now, a typical control characteristics of a single phase half-wave phase controller, AC voltage controller, is shown here. We can observe from the control characteristics and that the range of RMS output voltage control is from 100% of Vs to 70.7% of Vs when we vary the alpha from 0 to 180 degrees. Thus, the half-wave AC controller has the drawback of limited range RMS output voltage control. So it's between 70% and the 100%. We can't go lower than that. And we're going to solve the example in the next class. The exam is going to be, by the way, up to this point here, the on-off before the phase control. So the exam is going to be up to this slide over here. Okay. Thank you so much, and I would see you on Wednesday.